So today we'll not talk about CQL, we'll talk about reasoning and sort of particularly reinforcement learning for LLM reasoning. So at a high level, reasoning could mean many, many things and it clearly even today means different things for different people. But what I'm going to do today in this lecture, and also I should mention that it's very hard to kind of do justice to reasoning topics in sort of one lecture. This was also a trouble that I had for my own class this semester, where I was kind of covering similar content like 2 weeks ago, and I couldn't go over everything. But what I'm going to do today is to sort of give you at least one perspective on some of the trends in the field of reasoning. And for doing that, what we'll do is we'll restrict ourselves to solving math problems. So, if you're following all the news in language models these days, people have been really excited about solving technical questions like math and coding and scientific questions with these models. And one of the benchmarks people look at, for example, is this AIME exam, American Invitational Mathematical Examination. This is sort of an example question, from that particular exam where you kind of have to solve a certain sort of number theory question, for instance, and to solve this, these are some ground truth solutions for it. You'll have to solve this in natural language, where you kind of want your language model, for instance, to after seeing this question, produce a solution that looks like one of those solutions that you see up on the slide. So I took these solutions from sort of the ground truth, sort of the reference solutions that exist for this exam, but you would want your LLM to sort of be capable enough to, one, write a solution like this, and two, come up with the right answer finally. So that's sort of the goal for today. So what I'll do today is I'll give you sort of my perspective on, I'll organize the material in reasoning and especially RL for reasoning in sort of a particular way that I particularly like. And to do that, we'll start off from sort of the conventional way, or looking back at the conventional way of training language models. So typically when we train language models or just generally foundation models overall, the conventional paradigm has been to do next token prediction, meaning you take your data, you tokenize that into a string of tokens, token inputs, and you train the model with sort of a negative log likelihood loss to predict the next token that appears in the sequence. So in the context of reasoning, this would mean you would take the question, you would tokenize it into a string of tokens, you'll take the answer, which is from one of these reference solutions, tokenize that into a string of tokens, and then train the model to predict this answer string conditioned on the input question string. Now, to start to look at or start to understand why RL matters here, we'll start by asking this question of why does next token prediction of this form actually work? And again, answering this question will take it's an open research question, to be honest. But one perspective of looking at this that I particularly like is to sort of look at this particular equation, which tells you how well next token prediction works in general. So what is this equation telling me? It's telling me that if I train a model, if I train a particular model p theta, which is mapping some inputs x, like the question, to some output y, like the answer, this learned model is only going to approximate sort of the ground truth underlying model or the ground truth solution with an error, meaning with an error that is shown on the slide, which is p theta minus p star, depending on the size of the data that you used for training. So if you have a lot of data which shows you many questions and many answers, then ideally this error would be low and you would kind of approximate sort of a very highly capable expert at solving these questions. But in reality, it so happens that the amount of data that you have for a lot of these reasoning problems, and many other domains as well, you really don't have enough data to make this bound small enough. So you kind of end up learning models that are not approximating human level capabilities if you just do next token prediction. So there's actually sort of a lot of work that exists out there which studies the amount of data. And one of the interesting things that they tell you is if you simply keep taking high quality solutions of hard questions from the internet, and you train your model with some sort of supervised training, some sort of next token prediction, you will kind of not do really well because it's estimated that you are going to run out of high quality data of this sort by 2028. And clearly you have not gotten to a level where you can do great research with, or these models can just replace human researchers, for instance. This also happens in other domains, like for instance in robotics and embodied AI, where again data is very limited, which means that if you just simply rely on next token prediction alone, you'll not be able to get the ground truth sort of expert level capability in your model of sorts. So just to kind of give you a concrete example, if you just train models on current data and you ask them to solve this very interesting question from IMO 2021, Presumably this question exists in the training sets of one of these models, but if you ask sort of GPTs or OpenAI family of models to solve this, they're going to give you a solution that kind of looks very sensible in these settings. So, they're going to produce solutions that look quite like a solution that a human expert would have written, except that they end up missing the logic behind the answer. So in this particular question, if you need to prove that inequality that you see up on the slide, you cannot really go out there and start to look at individual terms of that expression. You have to kind of think about the whole summation as a whole, and these models. This is, I think, from an O series model. I think O1 that I kind of got the solution. It starts to look at sort of individual terms, for instance, and ends up kind of asserting its solution at the end, but it really kind of does not realize that it's actually making a mistake and does not correct it. So really what ends up happening with these current sort of supervised training paradigms, when you think about reasoning, is that they're going to produce a solution that looks very much like a legitimate solution that you could have written on an exam. It's just that that solution ends up being wrong and the logical content of that solution is not quite correct. And that's precisely something that RL tries to fix. And I'll hopefully try to show you some examples today of what kind of RL techniques come to rescue in that setting. So in today's lecture, I guess we'll talk about RL for reasoning. I roughly sort of characterized this in sort of two parts, or I broke this down into two parts. And these two parts are based on sort of timelines. So it's based on like stuff that came before sort of the DeepSeek R1 family of models came out. How many of you know what the DeepSeek R1 model is, actually? I'm just curious. Or have seen it, have played around with it. It's a model that was released, which is from a company in China named DeepSeek, which is really, really good at solving a lot of these sort of competition math problems or competition coding problems. It's sort of in a similar vein, a similar style of model as the OpenAI O series of models, or some of these thinking models that exist out there, like the Gemini thinking model or sort of Claude Sonnet thinking version, etc. So these are sort of models of the same family, and what we're going to do is we're going to talk about techniques that came before these models came out, which is early 2025, so January 2025, and some techniques that kind of have become much more prominent in the community after these models came out. So the first part of my lecture will be based on these classical techniques that I'm going to talk about. And I'll talk about techniques that rely on some form of imitation learning, which I'm guessing has been covered in the class. We'll talk about some techniques that look like offline reinforcement learning, and I'll talk about some techniques that look like online reinforcement learning. This is sort of my characterization of this whole space. In general, there's a lot of literature that has been coming out, so I'll probably miss out on some of them, but this is roughly a characterization that I think makes sense to think about. And after that, I'm going to talk about some modern extensions of these techniques into sort of this, into this thinking model kind of territory, where we'll talk about how can you take some of these techniques that people have built, before early 2025, and think about using them to train thinking models that have been doing really amazing right now. And there's some very sort of interesting things that need to change when you go from the left-hand side to the right-hand side in this particular setting. Okay, so I guess I already talked about the problem setup, but let me kind of just quickly go into a little bit of a detail and connect back to RL terminology. So we are going to consider reasoning, and in this particular setting, as I described earlier, you will be given a problem in natural language, and you have to write a solution in natural language. So what we can do when you think about this in the context of RL from an RL person's lens is you can think of this whole problem solving as an MDP, as a Markov decision process. And to do that, what you can do is you can think of the string of tokens that exist or string of words that exist in the question as sort of an initial state of your MDP. So it's sort of the initial state that your agent or your policy is going to start from when it starts to sort of act in the world. You can think of sort of this solution that the model produces, as being broken down into a sequence of steps. And these steps could correspond to actions, for example. So you can think of it as, there's a model which takes as input this initial state, which is the problem. It one by one takes in a bunch of actions, which are these steps, and at the end ends up with a particular answer. So in this particular setting, that answer is represented in this sort of, in this box that you see up there. And the answer is 8. And what you're going to do is you're going to reward the model with a sparse reward of +1 if this answer ends up being correct. And a reward of 0 if this answer does not end up being correct. So the real Markov decision process here is sort of state, going to a sequence of actions, and going to sort of a termination bit where the model produces an answer, and you get a reward at the end of it when if the particular answer is correct or not. So in RL terminology, this is a lot like a sparse reward MDP with a deterministic dynamics. What do I mean by this? Basically, there's no external environment in this whole process of producing these steps. There's no external environment that gives you a next state. All you are seeing is the initial state and these actions one by one, which tell you the next state of the problem. So I'll just draw on the board because I think, so this is your initial state. Your model takes as action, the particular step, the first step of the problem. It gets to state S1, which is nothing but the string of tokens in S0 and A0 concatenated with each other. So that's all S1 is. It produces the next state A1, or it takes the next step A1 or next action A1, goes to S2, and your next state S2 is just S0, A0, A1 concatenated with each other until you hit the final answer. So, you do this multiple times, you hit the final answer. Your model produces some answer, let's say 8. You get a reward, which is based on, whether 8 is equal to the ground truth answer or not. So you get a reward of R of 8, ground truth. This is either +1 or 0. That's your MDP that you're operating in. So that's a very good question. So the actions here could be infinity. There are infinitely many actions, but unlike unless continuous control, where you kind of have a fixed dimension vector of continuous values, which are also infinite, you have a variable length string of tokens, which are all discrete, but then there could be many of them. So the question is, what about questions where the answer is a proof or not a final numerical value? That's a very good question. I think we, as a community, haven't figured out the right set of techniques for such problems. So that's why we started off with sort of competition problems where there is a sort of a deterministic final answer in some ways. So we'll assume for now that we have a deterministic final answer we'll end with. Yeah, so the question is there a risk that we get to the right answer, but we take suboptimal steps? There is, and I'm going to be talking about that in this lecture, actually. Yeah. So that's sort of a basic sort of, reasoning MDP or a language MDP you can pose for studying reasoning problems in this particular setting. And at least something that I'm going to be sticking to in this particular lecture. Okay, so we'll start with studying some classical RL methods for reasoning. And what I'm going to do here is I'm going to cover one of my papers from NeurIPS 2024 that you see on the slide. This is the first bullet point. And why am I covering that paper? It's not because this paper invented a lot of the techniques, but because this paper actually did a lot of interesting empirical analysis of a lot of the methods that exist out there to kind of understand why something works and why something fails. So it's just sort of a nice way to kind of get a conceptual model, at least in my opinion, about all the sort of techniques in the classical reasoning space with RL. Okay, so what we're going to do is we're going to sort of try to understand how different methods or how RL methods for training for reasoning behave when we train them on different amounts of data. So we're going to do what we call a data scaling analysis in this particular segment of the talk. So the basic setup here would be I'm going to build algorithms that can be used to train reasoning models on a data set. Right? This data set will consist of some problems or these initial states that I described to you earlier. And we'll assume access to some oracle solutions because we need a way to check the ground truth answer because that defines the reward function. So we have a data set of problems and solutions that we're going to be training with. And what we're going to do is we're going to try to understand different classes of methods by evaluating how well they do when we train them on different amounts of problems and solution pairs that this data set gives us. So there's 3 axes we are going to look at when we think about training these methods on this data. We can train them with potentially ground truth answers on multiple questions. So we can take this data set of problems and solutions and train the model to produce the solution given the question, like what supervised fine-tuning or imitation learning does. So we can just do imitation learning on top of this data. We'll introduce a new method that we call rejection fine-tuning, which trains on many correct solutions for a given answer. So I'm going to write this method out here, and that'll be clear for you. So what you're going to do is you're going to take a model, pi of y given x. We'll take a question x from my data set. So this is my question or problem. So this is my initial state. This is my solution, which consists of a sequence of actions. What I'm going to do now is I'm going to take these questions and sample multiple solutions from my particular model, from my current model that I want to train in this particular setting. So I have a model pi theta. I'm going to sample multiple solutions conditioned on the question given this particular model. So this is my model that I'm training, the initial model. This is the data set. I'm going to sample multiple solution traces. What I'm going to do now is I'm going to take these traces, evaluate the rewards on each of them. So I'm going to evaluate R of y1, R of y2, R of yn. Why can I do this? Because I have this question in my data set, which means I have a ground truth answer y star for this question in my data set as well. Ground truth answer for X question. And what I can do is I can simply match whether multiple traces or multiple trajectories sampled from my policy, pi theta, end up in the right answer or not by checking checking whether the final number was correct or not. So what I'm doing here is I'm taking my initial model, sampling a bunch of traces or rolling it out in my environment, which is simply producing solutions from this model for each question, and evaluating the rewards against the ground truth answer. Now what I do is I take this particular set of y1 to yn's I produced, and I retain only those ones which ended up in the right answer. So I take the set S of y1 to yn, and I filter it to get some filtered set, let's call it S tilde, which consists of y's, so yj, such that the reward is 1. Meaning these solutions ended up at the right answer. Does this procedure make sense to people? Okay. And what I'm going to do now is, now I have a bunch of traces or a bunch of trajectories that ended up at the right answer, which means they're successful. So what I can do is I can simply try to train my model pi theta to imitate these trajectories. So I can train pi theta to imitate S tilde. So I'm just going to write it down here again. So my algorithm looks like this. For iteration 1 to some t that I can choose however I want. Sample, so step 1 is sample y1 to n from pi theta of dot given X question. The second step is filter and generate S tilde, which consists of correct correct y's only. And the third step is do imitation or do BC or SFT, depending upon whatever terminology you like, you can call that, on S tilde. So you're training the model now, pi theta, to produce only the y's that were correct. So that's sort of this particular approach. Okay, so this approach is what is called rejection fine-tuning or RFT, and that's why you see it on the horizontal axis up there, where what you're doing now is you're going to produce many solutions and try to filter for correct ones and train on them again. What happens now is you're rejecting the ones that were wrong, hence the word rejection, and fine-tuning just stands for fine-tuning, so RFT or rejection fine-tuning. The nice property about this approach is it's not actually asking you for Oracle solutions that a human wrote. All it asks for is solutions that your model can produce, which ended up being correct. So these are on-policy rollouts that are sampled from your policy, and you're simply filtering for correctness, which you can because you know what the reward function looks like. And the third axis here is actually full-blown reinforcement learning, where, in RL, when we train on data, we don't really need the data to be high quality or high rewarding. You've talked about offline RL, that's on your homework. You can learn from suboptimal data that does not succeed. And so you can kind of also think about, the third axis in all of these methods as methods which train on incorrect solutions or learn from traces or rollouts that did not succeed, that attained a reward of 0. So I'm just going to call them RL. So there are these three different axes along which you can sort of, train methods. You can scale your data, you can scale your model bandwidth, number of questions and Oracle solutions, SFT, number of questions and correct solutions by filtering or rejection, which is called rejection fine-tuning or RFT, and just training on any kind of data, which is reinforcement learning. So what I'm going to do in this lecture is we'll talk about how these different methods actually behave in practice, and that'll give us a sense of like what to use in what case. So the question is, are we forcing the model to come up with overly verbose answers? So here we are not really, the short answer is no, because here we are not really encouraging verbosity at all. All we're doing is we're simply sampling multiple traces from a model and train the model to find answers, train the model to sort of, closely mimic traces which ended up being successful in some way. So if the traces that end up being successful are those that actually need more space to be verbose, then it's going to incentivize you to be verbose. But if the questions that end up succeeding are not those, or the traces that end up succeeding are not the ones that end up needing to be verbose, then it's going to not incentivize it. So imagine that, let's say the question is 2 plus 2 is equal to question mark. Maybe one of the traces gets you an answer of 4, and there are some traces which are going to do this, which are going to count 2 plus 2 in 10 different ways. But most of the traces write down 4 right away. Then what you're going to do in this process is you're going to find traces which end up with a 4 right away, and you're going to train the model to produce 4 right away. That's the next token. So it's not necessarily going to happen that way. Okay, so the question is, if the method got the correct answer with the wrong sort of approach, then you're incentivizing the model to learn that. And the answer is yes, and that's why we'll see how these things behave in empirical results. That's kind of the next part of the talk. Yeah, so the question is, would the dataset be biased towards easy problems? The short answer is it does, yes, in some way. But the practical answer for this question is, well, in these cases, what you're going to do is you're going to potentially start with training the model on top of Oracle data or Oracle question answer pairs first with SFT, the first axis that goes up, and then do rejection fine tuning on top of it. So the model has some capability now to produce some answers for those questions, and then you start doing it. Great. So this was actually one of the slides which took me a long time even in my lecture back then. But a lot of the slides from here on are actually talking about properties of these methods actually. So the first thing we're going to look at is how does SFT behave? So training your model with like imitation learning on correct answers given questions that some human wrote. So when we're doing this work, we looked at 2 benchmarks named GSM 8K and math. These benchmarks now are fully solved. So, it doesn't make sense to sort of going forward benchmark methods on these benchmarks. But back then in 2024, this was like a year ago exactly. These benchmarks are very sort of representative of like useful methods. So what we try to do in this particular slide is we are trying to see how well SFT behaves and we're trying to compare it to RFT or rejection fine tuning that I described to you. We do that on top of multiple models, and here I'm showing you one result on top of the DeepSeek V2 model that is one of the best math models back at the time. And what I'm plotting here is I'm plotting the average test error of these models after fine-tuning with these SFT and RFT methods as a function of how much data we run fine-tuning on. So the more the data, the ideal picture is you will get lower error and you should be able to actually get better accuracy, right? Because you have more data, more coverage of questions like that. So that indeed does happen. So you do find that, error goes down as you scale up the amount of questions in both of these settings. But clearly, sort of the error does not go down at a very fast rate. Meaning, it so turns out that, the test error, if you try to like approximate the closest sort of function to this particular curve, it'll be the function that looks like d to the minus 0.15. Or d to the minus 0.05. So this particular curve that you're seeing, these are empirical measurements, but if I try to fit a smooth curve to it as a function of the data set size, that the exponent is going to be a very small number. Ideally, you would want this exponent to be really large, like d to the minus half, for instance, because this curve will go down very quickly, and with a reasonable amount of data, you're going to be succeeding at the particular problem, at this particular data set. But that doesn't happen in this case. So one of the goals that we then could have for a lot of these reasoning methods and RL methods for reasoning is to sort of push this curve as much as possible towards the left and towards sort of the x-axis. So push them down and towards the left. And the first result we saw to that extent was the fact that rejection fine-tuning or training on your own data, on your own correct solutions, actually gets you a much better test error. So you find that you can get the same test error on both of these benchmarks with RFT as you could do with 2x the number of questions and 2x the number of human written solutions for SFT. So what this tells you at a high level is that sort of on policy imitation learning, sampling from your policy and imitating the correct answers can be 2x more efficient in this particular setting compared to SFT alone or off policy SFT or just imitation learning alone. Okay, great. So that's sort of the first result, first takeaway to have here. But it so turns out that if you simply keep doing this over and over, it's not going to give you the best possible policy or the best possible model. So if you simply keep scaling up SFT on policy data, what do I mean by scaling it up? I mean, you increase this value of n that you see up here. So you just sample tons and tons of solutions and pick the correct ones and just start to, do BC on all of them. Turns out that that recipe does not actually work. So what happens is on policy imitation learning ends up hurting generalization if you do too much of it. And to show a result for it, I'm going to show you a plot here, which is showing sort of the test performance, so the same plot. But now the x-axis is the number of correct answers you get in this filtered set that I was describing to you earlier per question. So you can scale it up for how much ever you want. S tilde, the size of S tilde multiplied by a constant factor is shown on the x-axis, and we are plotting the performance of the resulting RFT trained model. The interesting thing to notice here is that, initially your error goes down. So as you do more and more correct solution traces, as you generate more and more of these correct solution traces, your error goes down, as you see initially. But then beyond a point, your error starts to go up in this particular setting. So you find that beyond a point, you hit diminishing returns, and there's no way you can simply generate more solutions from your policy, mimic them, and get better performance. And in fact, the error even goes up on some of these data sets that you see up here. It's the number of, you can think of it as S, the size of S tilde. So number of correct solutions you retain per question. So the question was, what is the x-axis? The x-axis is number of S tilde. So the plot, it's basically S tilde times 8k in the plot, because, that's the number of prompts that you see up here. But yeah, it's just a constant multiplier, which stays same for all the points on the particular plot. So that's a great question. So the question is, when you scale S tilde, which is for RFT, do you do deduplication? The answer is yes. And I actually removed that detail from my slide because I thought it would be too much details. But since you asked it, the answer is yes. You would often, when you do this process, you would often deduplicate S tildes. There's a lot of mechanisms for it. People can do just edit distance based sort of rejection as well. So keep the, sample more than n. So one of the recipes people do is sample more than n, like 2n. And retain the n of them, which actually seem to be maximally diverse. That's something people do a lot of times. So yeah, you do that kind of thing. Great, okay. So what this tells us at a high level is that fitting on self-generated data on a limited number of initial states actually hurts generalization of the model. So if you recall the picture that I drew earlier, which I erased, where there was an S0 and your model took an A0 and went to S1, you can think of this as basically training on a set of S0s and evaluating on a new set, on a new test problem. And turns out that if you train too much on a particular set of S0s in this particular way, you end up hitting the generalization bottleneck in that setting. Okay, so why does this happen? And this is sort of the picture that I'm going to talk about. And I'll connect it to some of the interesting concepts that we know in imitation learning right now, which is this picture of spurious steps. So so what we're going to do is, we'll move away a little bit from like examples and look at pictures. And what we'll do is we'll plot these pictures, as I was describing to you earlier, as this little trajectory in an MDP. So you have prompts as initial states, and you're producing these steps one by one. They take you to the next states, and then eventually you end up at the answer. So it so happens that when you sample a lot from your own model and train on it on policy, like you sample from your policy and train on it, you'll often find that there are some of these traces which end up having steps which are spurious in nature, steps which actually are incorrect, but they just somehow don't affect the model's generation. So I'm going to show you an example, but basically these are steps which would take you to a regime where you're maybe doing a wrong calculation. Somehow, you get there. Maybe on this particular trace, when you're sampling from your model, you end up recovering from these traces, so you end up at the correct answer. But maybe in reality, these traces are actually harmful. So just to give you an example, let's say this is a little arithmetic problem. It's from this GSM-8K dataset. One interesting example we found, which is the most stark example of this particular issue, was there's a solution from the model which does some calculation. Then it says that the total amount of money needed is like 100 times 2, which is 200, and it reverses its calculation in the next line. So the true calculation is 100 by 2, but it ends up saying 200 and then sort of goes to 100 by 2 right away. So what ends up happening is this particular step that exists in the middle, where it's doing 200, is sort of a spurious step. It's a step that is not needed. It's an incorrect step that exists in the solution. You end up still at the right answer in this particular rollout, but this step shouldn't be there in reality in that particular setting. So that's a spurious step in this particular setting. So the question is, the step is always a sentence. For now, you can imagine it's always a sentence in this particular setting. There's no universally agreed upon definition to it. So this is a very sort of, I guess in the second part of my talk, I'm going to show you some examples where the step is not at all a sentence. It's a full block of things. So yeah. That's a great question. So, so the question is this the main cause of increase in error, and can you not measure it in some way? Turns out that the answer to both is yes. It's one of the main causes for increase in error. Can you measure it in some way? At least normal notions of fitting the data won't tell you this. That's a great question. So the question is, can we associate the overfitting problem with this? So you can actually measure this. In the paper, we did measure this. We measure the amount of spurious steps that you see, and it grows on over time. Obviously, I cannot give you a proof that this is the only cause, right? I can give you a proof that this should be a problem. I cannot give you a proof that this is the only problem, but this is sort of one of the big problems that you see. So the question is, how do you find out if it's a spurious step? In our experiments, we do it in a particular way, and that also dictates a lot of methodologies that I'm going to show you in a second. So this particular method so the question is, do you sample entire trajectories? This particular method samples entire trajectories. You can sample parts of trajectories if you want it to be, but I think it needs some advanced machinery that I think can be done based on what I'm going to talk about in the next slide. That's a great question. So the question is, do you overfit to a certain class of methods that got to the right answer? In a way, the answer is, at a high level, yes, with the caveat that I don't know how to define what a method means, right? So you can call a method that, so just seeing this example, one can say that the calculation of 100 times 2 is a methodological phenomena that the model wants to do to be able to then succeed and then realize that it was wrong. You can also say that, really the method here is nothing but just doing a bunch of arithmetic. So it really depends on what you define that, and I think it's a semantic question at that point. But yeah, so from a very sort of symbolic perspective, one can say that there are a set of tokens that maybe still lead you to the right answer on the training set, but may not actually help you do the right thing on the test set, on a test problem. So this is very similar to the problem of causal confusion in imitation learning, actually. I'm not sure if causal confusion. Okay. Never mind. But basically, there's this problem of if you produce a bunch of stuff in your policy that might be bad, like these spurious steps, you might just not learn to imitate the expert in the right way possible. So maybe you actually end up at the right answer, but you're learning these incorrect associations. That's basically the gist of this problem of causal confusion that people in imitation learning know a lot about, actually. Okay, so how can we address this? And that's where RL comes in, and that's sort of the third axis of using incorrect data or incorrect rollouts for learning. The simple idea is, as many of you already asked questions about, assigning some notion of a credit to a step. So if I can understand, what is the utility of every single step or every single state that my policy generates, then I can kind of somehow use that notion to filter off these bad kinds of solutions in some way. So that's exactly kind of what we do, or what RL for reasoning tries to do at a high level as well. So identifying these spurious steps and eliminating them in some way. So the way to do this is the following, and this ties back to a lot of concepts of value functions and advantage functions that many of you are probably familiar with. So I'm going to start with an illustration, and then I'll write down the exact math for what this means. So let's say I gave you a particular rollout or a particular trace, so again, starting from a prompt, adding these steps or actions and going to a final answer, which maybe ended up being incorrect. So it's shown as a red dot. What I can do now is, I can try to identify whether a step is spurious or not by taking these particular prefixes, or taking these particular states that were basically concatenating all the tokens so far and doing what you can think of as rollouts in a way. So I can ask some model to try to complete the solution given a prefix of a generated solution. So, for example, in this particular setting that you see on the slide, I have kept the first 3 steps the same, and I'm asking a separate model or a separate rollout policy to try to complete the solution given this particular prefix. I can do this, so if I do this and let's say the rollout ends up succeeding, so, many of these rollouts end up at the right answer, then likely the prefix was not too bad because clearly for this particular rollout policy, it did not end up affecting any of these, any of its, problem solving abilities. On the other hand, let's say if I ended up at a totally wrong answer conditioned on the prefix that you see up here, clearly something is not okay here, and clearly there's something wrong with the prefix that you're seeing up here because your rollout policy could not at all succeed, conditioned on that prefix, even after doing many possible rollouts. And if I ended up succeeding sometimes and sometimes not, maybe there's still some issue. Maybe it's not the best thing you can have, but at least it's slightly better than always failing that you see up here, for instance. So this basic principle of doing rollouts and estimating some notion of expected success in the future can kind of tell you something about what is wrong with the current prefix that you are particularly operating at. This is also very similar to a value function, right? Because this is basically computing the expected future 0-1 reward that my rollout policy, that this orange policy gets when it acts in this particular MDP. So the question is, the spurious step on the previous slide, is that actually irrelevant or incorrect? Or irrelevant slash, it's incorrect clearly because, the step is not incorrect in its own right, but it is sort of irrelevant in a way. Imagine for a second that if you pass to a language model a million irrelevant tokens and ask it to sort of dig out the information that actually matters, that can be a challenging problem on a test set. So that's why even if a step is irrelevant, it can be a problem for the model. Okay, so we did these rollouts. We computed the expected value of how many times can I succeed. And that resembles something that looks like a value function of sorts. And why is it a value function? Because if you sort of write this down in a bit of math, so let's say if I define the problem or the initial state as X, each of these steps as y1s to yn's. I guess there's a bit of a notation mismatch here. Y1s to yn's are independent rollouts. Here, the yi's I'm showing are basically each step or each action that you take. So if you define a quantity that looks like the following, it's basically a Q function. So what is this quantity? It's telling you the Q value for your particular rollout policy, pi tilde. So the policy which is trying to complete the solution, rollout policy pi tilde. I'm computing its Q value at a given state, given by the initial state and the prefix of the solution so far, and given an action, which is the current step that your policy adds. I can define the Q value here as the expected long-term reward, meaning the expected 0-1 reward that I get under my rollout policy if I start by executing, if I start by getting actions I plus 1 to L from this rollout policy. So what's the Q function? A Q function, just to recall, Q pi, I guess it's subscript pi. Q pi of SA is basically nothing but R of SA, or I guess depends upon how you write this, but it's basically the expected discounted reward that you get starting from t equal to 0 to, let's say infinity in general, conditioned on S0 being S and A0 being A. This is the definition of a Q function. In this particular setting, we are assuming discount factor is 1, so gamma is set to exactly 1. And the reward that you get is only at termination, so there's 0, 0, 0, 0 until you end up hitting the final answer. So that's why you see there's only one expectation up there. And this expectation is computed under policy pi. So you roll this policy pi out from there on. There's one minor detail here. You typically have R of SA plus this thing, because you roll out the policy from the next step and you sum up the reward at the current state. In this case, it doesn't matter because R of SA is equal to 0. You only get a reward at the end. Gamma is set to 1. So essentially, the thing that you see up here is essentially an expected future reward starting from a given prefix, which is the state, at a given step, which is the action, and the rollout is performed under pi tilde that you see up here. Okay, so the question is, would you use the same policy to roll out those other trajectories? So in principle, this equation that I wrote is agnostic of which policy you use to do the rollout. So there's been actually no, so I have a belief about this answer, about this particular choice of the policy. So in my opinion, the policy that you're doing rollouts with should be a different policy compared to the current one. Otherwise, it can fail in the same way. There's some work in literature which argues that even using the same policy can actually be good enough. I think we haven't seen an apples to apples comparison, given the sort of scale of experiments, which definitively shows one way or the other. I think most of the evidence that exists right now points towards the benefits from having a different policy, because that makes sense also. But I think there's a part of the community, especially sort of the NLP community, which kind of does it using the same policy and finds it to work reasonably fine. That's a great question. So the question is this similar to trajectory stitching and advantage weights? It so turns out that the answer is exactly yes. It is very related to that. I don't think I have a discussion of this stitching angle in my slides because I think it would have been a bit too technical. But yeah, if you check the paper, you'll find exactly it talks about sort of stitching in this particular setting, and it's very related concepts. So yeah, you can think of it that way. Okay, great. So this is the definition of a Q function, and once you've defined this Q function, it so turns out that you can use this Q function to now tell you whether steps are spurious or not, or are good or not, in the same way as defining advantages would have done. So I'm pretty sure you talked about sort of advantage weighted regression as an offline RL method. I'm going to do something very similar to that, but just sort of to kind of spend 1 minute on the definition of the advantage here. So the advantage function typically means QSA minus B of S, that you probably talked about. So A of SA under a given policy is Q pi of SA minus B pi of S. In this particular setting though, the dynamics are deterministic, and the state is simply a concatenation of the previous state with a new set of tokens which define the step that is added in there. Hence, what happens is like you can define the advantage as Q value of the prefix until step I minus Q value of the prefix until step I minus 1. That sort of serves as the same notion of advantage in this particular MDP. So that's why the definition you see up there is Q minus Q and not Q minus V, but it's sort of basically the same thing. So once you define it in this way, you can actually compute these advantages for every step. So you can compute advantages by subtracting the Q values for consecutive steps, one from each other, and you'll get some positive and some negative numbers in this particular setting. Just really depends on how many times can you succeed. And once you have these advantages, they are a measure of how well how much a particular step contributed to your ability to be able to succeed from that particular prefix. So if step 2 ended up like sort of reducing the advantage, that means your Q value at step 1 was higher than Q value after step 2 has been executed, which means step 2 is probably not that good of a step to have in order to be able to succeed eventually. So a negative or a low advantage means it's sort of a bad step or a kind of a spurious step, and you don't want to necessarily learn from it. A positive advantage means it's a good step, and you probably want to learn from it someday. So this is sort of supposed to answer the questions about like how do you identify spurious steps in some way. So the question is, are we fitting a Q function? It's a very good question. Turns out that in the literature, there's been two kinds of work. They explicitly fit a Q function like quantity. It's what's called, so in the NLP community, this is what's called a process reward model. Process reward model. So I'm guessing since you covered DPO and RLHF, you've talked about reward models, which sort of give you a score for like particular question and answer. This is sort of giving you the score for every step, and hence sort of like scoring the process, and hence the word process reward model or a PRM. I don't necessarily think that PRM and Q values are exactly or should be semantically the same thing, but that's kind of what a lot of the NLP people call this. But yeah, you can kind of train that. But there's the other class of methods which would simply use rollouts the way I talked to you about to estimate advantages, and we'll see what that means. Yeah, that's a great question. So the question is, how does this help models learn general problem solving strategies? The rough answer is ultimately what ends up happening here is you are breaking down the success of a particular long trace into sort of successes of individual steps that appear inside of it. And that can be a useful thing to know, because now, presumably your model can realize that, okay, let's say it has broken down a problem into 4 steps, or 4 high level plans. If it can also localize which step is kind of going wrong, it can actually, better learn that step as opposed to sort of, just vaguely thinking that, okay, a step 3 might be the cause of the problem when it fails, whereas maybe it's actually step 1. So it helps you just learn, sort of in a more, so ultimately you need to have some data for learning, but then this is sort of vastly improving your data efficiency in some. Yeah. Great. Okay. So the next step is going to be to use these advantages for training. And this is where sort of a lot of the methods that I talked about also will come into picture. So the first thing is just going to be to filter by advantages that I just described. So you can take a bunch of traces from your model. And, I still have the RFT algorithm here. So I'm just going to I'm gonna write it down as 1 to n, sample from pi theta. You can take this, you can take the RFT algorithm, you can sample, you can sample from your model, an on-policy trace potentially. You can take every step, do these rollouts that we talked about, use them to estimate advantages, and put this into your training data set for doing imitation learning or SFT, if this particular step is correct. So what does that mean? That basically means that you are taking a particular trace and you are checking for, at a step level, whether the advantages are positive. Even if that particular step comes from an incorrect solution trace, you're going to put that into your training data set if that step itself gives you a high advantage. On the other hand, let's say if that step itself comes from a correct solution trace, maybe there's a particular step here which gets a low advantage or a really negative advantage. I'm going to just throw it away in some way. So this is very much reminiscent of advantage-weighted regression, except that here, rather than doing exponentiated advantages, which I'm guessing was covered, we are doing sort of like filtering on advantages. That's sort of the basic idea. You can also do exponentiation of advantages, so you can train on everything, but multiply the loss by e to the a. That objective, I think, requires a lot of tuning, and if you can only run one experiment, you probably prefer this objective over e to the a in general. That's a great question. So the question is, do you only train up to the good steps on an incorrect solution? The answer is not really. So we initially thought that that's kind of the only way to train here. And we did a concrete ablation studying this as well. The answer is, well, you never really train the model to, so in this particular setting, you're not, let's say a particular step gives you a higher advantage. You're not training the model to produce this step and then this step. All you're training is to produce this step conditioned on the prefix so far. So your loss looks like train the model to produce AI given SI and not the previous actions or the previous steps that you see up here. So I'm just going to probably just draw it here because I think it's easiest to draw it. So think of it as this way. You had X or S0. You took A0, you went to S1. You are taking A1, to S2. These are steps, and this is the states. You're not, so let's say this state got an advantage which is really positive. So A of S1, A1 is really positive, and A of S0, A0 is really negative. What you are going to do now is you're going to not necessarily, so what I'm not saying is train your policy to produce A0 given S0. You're not going to do that. You're going to just train the policy to produce A1 given S0, A0. So that's all you're trying. Or, I wrote S0, A0. This basically just is equal to S1 because you're concatenating steps. But that's kind of the thing you're going to incentivize. So you're only training on the steps. So the question is there a separate prompter that keeps prompting the model when it acts here? The answer is not really, right? So if in general, when you do RL, we never really train the policy to sort of, we train a policy, to produce individual actions, like in offline RL or in imitation learning. We train it to produce A1 given S1, A2 given S2, and so on. But when it acts in the world, it just acts and produces a giant string of or giant sequence of actions in one go, right? So you can train the policy on different segments of steps it's seeing, but when it's deployed, it's going to just produce one action. Then the state S1 is going to be simply the whole tokens in the question, tokens in the action, tokens in the step so far, and that's S1. And you're going to now the same policy can now continue on and produce the next step. So it's not going to be prompted in any way. It's just like going to be producing the whole solution in one flow, except that now you're just training it in a way that you're breaking them down into steps. So really, there's no notion of like a separate actor. So the question is, do you only train on a step because of the Markov property, because you don't care how you got there? In a way, the answer is, or actually no, because in some ways your state S1 consists of all of your history, right? So S1 consists of, so S0 is a problem. A0 is, let's say, step 1. And S1 in this case is basically problem concatenated with step 1, right? So in some ways, you have preserved all of your history in this case, and it's a non-Markovian policy that you're learning, except that here, the reason why we do this at the step level is because now we can better understand which part of the solution actually, caused me to derail if it did. So there's no notion of like independence. It's not like given S1. So, okay, in this particular setting, given S1, sure, action A1 is all matters, but S1 and S0, A0 are the same. So it's depending upon the way you look at it, it can be called a non-Markovian policy as well, because it's conditioned on the whole history. But in this particular setting, if you define S1 as concatenated states, it's a Markovian policy. So the question is, if your Q value is really, so if your Q values are really negative, but your advantages are positive, would you put it in the training data set or not? Yeah, that's a great question. I think we tried this with like, so we did take traces which were incorrect, and we took we put the steps which were actually good from them into our data set, and that was fine, except that, like, let's say if there are traces where everything is just a zero, like there's no way, like there's no prefix of that from which you can succeed at all. The advantages are also small and the keywords are also small. Turns out that if you filter them out, you might do a little bit better. But again, I don't have a very, very concrete like result I can show you here, so I'm not gonna like tell you that this is the way to go. But like it seems like to a large extent, the sensitivity does not exist in some way, because the prefix is the culprit then, and you're training only A1 conditioned on the prefix and not training the model to produce the prefix at all. Okay, great. So that's the first option. So this is a lot like filtered imitation learning or advantage weighted regression. The next thing, okay, before that, I can show you some results here. So this actually ended up addressing that error going up problem, at least to the extent that we were able to train models. So here again, I'm plotting number of correct answers per question, and you find that the advantage filtering did help you compared to sort of the RFT approach, which was going up before. So it does actually, and we did measure the number of spurious steps according to some heuristic definition of how we can evaluate this, like how we can probe this, and it seemed like just from a qualitative perspective also the number of spurious steps actually kind of reduced in some way. Okay, so the next thing is, how can you use this for offline reinforcement learning? And this is where sort of DPO based methods come in. So there was a question about this earlier in the class. So you can also use them you can also use the same principle for doing DPO actually. So the idea in DPO is sort of slightly different from computing this advantage exactly, but uses the same protocol that I described to you earlier, where what you're going to do now is you're going to take a solution from your base model that you're training. Maybe this is incorrect. And so far what we did was we found out steps that were useful and retained them in some way or the other and discarded everything else. But what we can do now is we can do these rollouts, and rather than sort of throwing away, or throwing away these rollouts or just using these rollouts to estimate the advantage, what I can do is I can instead take a rollout which ended up succeeding, with a shared prefix, take the solution trace from my model which did not end up succeeding, and construct a preference pair out of them. So I now have a preference pair which looks like, some prefix followed by some correction, which is good, and some prefix followed by sort of like some steps which are actually wrong. And I can throw this into a DPO training data set in some way. I can also do the same thing with like sort of a correct rollout. So if let's say I have a correct rollout from my base model, I can still do these rollouts, and maybe one of them will not end up succeeding, potentially, from my rollout policy, and I can basically put this thing as a preference pair into my training mix. So the nice thing that is happening, or there are two differences that are happening here, right? In some way, I'm still realizing in this process that prefixes are shared, and really the difference between correct and an incorrect rollout comes from that little segment that you see, beyond the prefix in these settings. That's the first thing. And the second thing is, rather than the previous approach of filtering by advantages, I'm actually retaining the whole steps that appear in this rollout distribution. So I'm not simply using these rollouts like the orange colored dashed lines to compute advantages, but I'm retaining them and I'm training on top of the tokens that appear in that rollout as well. So the DPO loss, I guess I don't have that on my slides, but I guess probably I don't need to necessarily write that down. But it's basically just a matter of like the same old DPO loss on top of these two segments of solutions that we talked about. Yeah, great question. So the question is, do you want higher quality text or do you want sort of more diversity? I think the true, I should mention that like, this is something that we have tried to formalize. So there's like an exact equation that you can write down, and you can be like, okay, I want a policy to do these rollouts, which maximizes this expression, sort of thing in one of the papers. I think that kind of balances in some way diversity and high quality. So imagine for a second that your model is really bad. So let's say your model mostly produces incorrect traces. then you want a rollout policy that can actually somewhat succeed, because otherwise there's no notion of a success that you can learn from ever, right? You've only seen failures. How can you actually even learn to solve that problem if you only see failures? On the other hand, let's say if your model is kind of decent, like 50% accurate, but it's like, not as good overall, like it's not the best at solving problems. In that case, maybe all you want is just diverse ways of solving the problem such that you can see what ways you're more prone to failing. So you care about sort of coverage in some ways. So really the answer here is, like every single problem in RL, there is some balance between exploration and exploitation you kind of want to do, which is high quality text or high quality solutions which solve the question correctly, and being more diverse in some way. I think the exact expression for this is actually something you can also write down, and I'm not going to cover today, but yeah, it's a trade-off between them. Yeah, so they basically used to train DPO. So like so far, I guess, okay, actually let me just write that algorithm down for everybody's understanding. So what you do is so that is the RFT algorithm. And now what we are going to do is we are going to simply do the same process. So for iteration in 1 to t, I'm going to, sample y1 to n from my current policy, given any question. I'm going to now do these rollouts. So I'm going to, do rollouts and, construct the preference data set dpref. In this case, it's basically those preferences. And now what I'm going to do is I'm going to run or minimize DPO loss. That's kind of the main algorithm that you're going to do. And the dpref consists of, prefixes generated from your current base model, and the traces coming from sort of, one part of it is from the same model that you are training, pi theta. The other segment, the other part of the preference pair comes from the rollout policy. That's the orange line. So the question is, given a sample trajectory, how do we segment into steps? So in this work, we just used sentences. So we just said, well, sentences, we're going to break them down into steps from after every sentence. In general, I think it depends. It's a thing that you can bake into your model. So if you have played with, for example, OpenAI models, you'll see that they often produce responses that look like, step 1 in sort of markdown, like a very big step 1, and then they'll say a bunch of stuff, and then step 2, and they'll say a bunch of stuff. So you can use that sort of notation. Oftentimes, it's so happening that as these models kind of get better at basic instruction following, you can just prompt them to produce responses for complex questions in a particular stylistic fashion and use some heuristics about that style to partition things into steps. So for instance, you can just tell a model, well, I want an answer that, for this particular question that, that never uses the word step, that always produces a logical block of calculation, puts a horizontal line and then pushes the next logical block and so on. And it'll most likely do it for you, which is something you can also do during the course of training. So you can just prompt them to kind of produce solutions in a particular way and then define steps accordingly. There's no universal definition. So the question is there a convention to produce special tokens for generating steps? I think that I've not seen a very, very clear convention that is universally used all the time. One convention that we have been using that I've seen many other papers use, but there are still outliers for this, is they would produce like step #1, : and then say something. And that could be a bunch of lines as well. In this work, we used lines. In a follow-up thing, we had used this like step notion. So it really depends on like up to you, really, I think. Yeah. Okay, cool. Any questions on the DPO part in this case? So this is the DPO version of the algorithm. Great. Okay, so you can do this and put this into your data. So if you go back to our plot from before, if you measure how well does such kind of an offline RL method do, what ends up happening is, okay, I guess these were supposed to be GIFs, but anyways, so I'm now plotting the test error as a function of number of questions that existed in my data set. So, so far we were looking at number of correct answers per question for a lot of the plots in the middle. But now I'm back to the plot where we are plotting the x-axis as a function of number of questions in the original data set. And you find that compared to, and now there are two models here. One of them is like a Llama 2 model. So this is probably tells you how old this work is at this point. It's a year old, but Llama 2 is feels like a long time ago. And then DeepSeek V2 models as well as, DeepSeek V2 models. And what we are finding in general is that compared to the base SFT method, where you were just training on human written solutions, you can get up to an 8x boost in the amount of data that you need for training. So the dashed line here is this per step sort of DPO algorithm that I talked about. And you see that it can get you the same test error with like 8x fewer samples than like training with SFT on like human written data. RFT was 2x for recollection. I removed that line here because it would have been too cluttered. But in general, like this 8x also holds true for Llama 2 roughly overall in this setting. Yeah, so the question is, what is pass at 5? That's a great question. You can think of pass at 5, I guess for understanding this slide, it doesn't matter, first of all, but in general, you can think of pass at 5 basically as saying, if I gave the model 5 chances, can it succeed even once out of those 5 chances? So it's sort of a way people evaluate models, because it's kind of telling you that, okay, maybe the model could not succeed in one try, but if I give it like n tries, maybe it can succeed. And that's what pass at n means in the setting. It doesn't, I mean, I don't think for this particular result it matters so much. The main thing to look at is this 8x kind of boost in data efficiency that you see up here. Okay, so the high level takeaway here is that if you do offline RL with sort of this per step notion of like credit assignment that we talked about, you can actually do you can actually get a lot more data efficiency boost compared to imitation learning. So for the same amount of data for the same base model, for the same base model and for 8x fewer questions, you can do similar, you can get the same performance with RL in this setting. Yeah, so generally I've seen people use 0.6 as the temperature for a lot of the, so the question is, what's the recommended temperature to use? I've generally found it to be 0.6 is what most people use. I don't think that there's something that's like set in stone. You can always change it in some ways. Solid line, so the question is, what's a solid line? That's just SFT on like human written solutions in this setting. There's no per step advantage in that line. Yeah. And the per step advantage one was actually the one I showed you before. I removed it here because sort of like this is the kind of maybe the ultimate kind of result in some ways from human data to a kind of self-generated data of sorts. But yeah, it's like 2x with the per step. Yeah. Okay, so the final thing final main method, and then I'm going to just talk about what people are currently doing very briefly, and I'll end the lecture at that point. But the final thing we can also do here is online reinforcement learning. There's two ways of doing this. Sort of the most basic recipe for doing this is actually to not use any of this advantage, but sort of generalize this kind of basic RFT algorithm without advantages to online RL. So how do you do that? You can basically just, take your model, similar to like how we sampled a bunch of traces from my current model or current policy and filtered the right ones. Rather than filtering, you can just train it with like on policy RL. So you can just generate rollouts from your current policy, which might be correct or wrong. You can reward them using like the reward function by just checking the answer against the answer that the model produces. You can penalize it if it does not produce an answer. You can penalize it if it violates format. There's a bunch of like reward shaping things you can do. And then you just like train your policy to maximize this reward using policy gradients. So RFT we were explicitly filtering and training with SFT. But rather than doing this filtering or training with SFT, you can simply run on policy reinforcement learning, because all in this formulation is just state, action, there's an MDP, there's a reward, and just do R on top of it. So, you can simply write the policy gradient equation. So that basically just looks like grad log pi times the reward that you see up here. And you can just run that on your problem. There's also a lot of work which now tries to kind of go beyond the basic reinforced style policy gradient and goes to sort of methods like what's called GRPO. It's nothing but just an extension of like the basic PPO algorithm in this setting. So the PPO algorithm, I guess I'm going to say a few things. Like PPO algorithm uses a learned value function. The GRPO algorithm replaces that learned value function or learned Q value function with simply this rollout based estimation of advantages. So the same old basic RL recipe applied on an MDP that looks like the thing that you see up there. So a trajectory that looks like the thing that you see up there with a 0-1 reward. Okay, and what you can also do, and this is something that finally you can do, is you can also do per step advantages in online RL. That's kind of the final method that you can apply. So in this setting, you can take a solution from your base model, or take a solution from your current policy that you're training, or over the course of training. You can do these rollouts if you want to. You can use these rollouts to compute advantages. And rather than doing these rollouts, you can also potentially do something slightly different, and which is basically to train a reward model-like thing to fit to these advantage predictions, or fit to these Q value predictions and then compute advantages. So this is very similar to sort of the RLHF work that you probably saw. except that now this is a reward model that is rewarding every step of sorts, or that a reward model that's producing the Q value for every step or the advantage for every step, as opposed to producing a reward for the whole sequence that you are seeing. And once you have these advantage predictions that you can fit to a network, you can query this particular, so for any rollout that your policy produces, you can query the advantage predictor that you have trained to reward every single step in this particular policy generation. And once you do that, what you can do now is you can simply, take your network, produce these advantage labels, and optimize for reward that you're getting at the end, plus these advantages that you see up here in this setting. Yeah, that's a great. So the question is, how generalizable is reasoning? When you train on math, does it improve on GSM-8K? So it turns out that if you train on math, it does not improve on GSM-8K, and many people have shown it. But if you train on a bunch of mixture of prompts, which are of varied levels of difficulty, you can actually get there. So this is precisely the recipe which is being used in or not this one, but the basic online RL recipe, which I talked to you about earlier. Used to train all of these, or many of these thinking models who have, which have like open, open recipe descriptions. So this online RL recipe is kind of used to train the DeepSeek R1 model, for instance, and that kind of does generalize to a fairly good amount of extent. It doesn't also generalize to every single problem out there, but to a fairly good extent it does. So you can compute these, advantage predictions. You can fit them to a network, use them to produce these rewards for every single step, and that's sort of the more advanced way of doing online RL. With this particular thing. So we had a work that we call process advantage verifiers here. Process because, it's rewarding every step. Advantage because it's fitting an advantage function. And a verifier because, somehow in the domain of reasoning, reward models are referred to often as verifiers. So if you see that word come up, it's just synonymous to a reward model of sorts. Or in this particular case, even you can think of it as a Q function or a value function of sorts. So, but that's kind of the name of the method. And, we find that in general, so I'm going to skip some of these details, but in general, if you do dense reward RL, like process reward or advantage-based reward RL, you find that you can kind of get to a much better accuracy compared to sort of what's called ORM RL, or just 0-1 reward RL, like the sparse 0-1 reward provided at the end of the trajectory. So this is sort of the basic recipe that a lot of the current work is using. This is sort of the advantage-based verifiers recipe. And you can kind of see that you can get a bigger boost in sample efficiency, as well as in terms of just absolute performance that you see up here. Also, these numbers kind of look small, but with 2B and 9B models that we were basing this off of, apparently this is sort of the best result that you can get on certain data sets that we tried this on. So it's about 5 to 6x sample efficiency boost and about 6 to 7% absolute performance improvement in this particular setting with the dense advantages in some way. Okay, I'm going to skip some of these things, but at a high level, we are also seeing now these newer thinking models that have come up, where basically these models can just think for longer and produce a better answer. This is sort of the DeepSeek R1 family of models, the OpenAI O1 family of models, or O series of models from OpenAI. In my opinion, really these are trained using very similar recipes that I just talked to you about for this whole lecture. Except that there are some small changes that happen in this process from pre these models era versus these models. So the RL training objective has remained the same. So there's some minor details, like there's this new method called GRPO, which I just describing. It's basically PPO with some tweaks. There's also some other methods like advantage-induced policy alignment. You don't need to know what those methods are. Just think of them roughly as policy gradient methods done with slight tweaks overall. But what has changed is that the action space in a way has changed for these models, in my opinion. Now, this is a very kind of crude statement to make, and to be really rigorous about it, I think the statement sounds wrong, because these models do actually produce token by token, one at a time. But these models, the base models on which we are doing RL, have become better at being able to kind of implement interesting kind of meta procedures. Like, these models can actually produce a solution, maybe go out there and then try to verify the solution they have produced, maybe then backtrack to a particular point and do something else from there. And you can think of this as just yet another version of defining the step. These models can produce more interesting steps than just going out there and calculating yet another quantity like the models previously could have done. So it's just a better notion of a step or a better action that these models can sample when you run all of these algorithms on top of them. And once you do that and you give these models a longer budget to act, so if you tell these models that, okay, there's no limit on how many tokens you can think, you can sample during the course of RL. You can maybe sample solutions which are really, really long, but just get me the right answer. If I give these models that playground to kind of sample more and more tokens, turns out that RL training algorithms with these two bullet points actually give you much better performance. And that's kind of what we see with these current thinking models right now. Turns out that if these models are, if you do a counterfactual experiment where you take models which are not capable at doing, implementing like basic sort of answer checking or verification or generating a better answer, turns out that you cannot do good RL with them right now. So really nothing has changed in terms of like the high level techniques that I talked about, except that the base models have become more interesting in a way that they can sample interesting kinds of steps to train on. And that has led to some of the most amazing results that we are seeing right now.